Hello and welcome back. Today we will have lecture 5-2 on Fourier Transforms. The objectives are to review several examples of finding the Fourier transform of a given signal x of t and to find the response to an LTI system using Fourier transforms. Recall from the prior lecture that the Fourier transform x of j omega of a signal x of t is x of j omega is equal to the integral from negative infinity to infinity x of t e to the negative j omega t dt. The inverse Fourier transform x of t of x of j omega is given by x of t is equal to the integral from negative infinity to infinity x of j omega e to the j omega t d omega divided by 2 pi. In class activity 1, find the inverse Fourier transform of x of j omega equal to t rect omega t over 2 pi. So the first thing we should notice is that x of j omega is band limited. And band limited means that x of j omega is equal to 0 for some omega, absolute value of omega greater than pi over t. So if I make a sketch for x of j omega, what I have here is my rect with an amplitude of t and the band limits between negative pi over t and positive pi over t. So x of t is equal to the integral from negative infinity to positive infinity t rect of omega capital T over 2 pi e to the j omega t d omega over 2 pi, which equals t over 2 pi times the integral from negative pi over capital T to pi over capital T e to the j omega t d omega, which equals t over 2 pi e to the j omega t over jt evaluated from negative pi over t to positive pi over t. So this equals t over 2 pi times the quantity e to the j pi lowercase t over capital T minus e to the negative j pi lowercase t over capital T divided by j times lowercase t, which is a sine function times t over pi t. So this is t over pi lowercase t times the sine of pi t over capital T, which can also be written as a sinc as the sinc of pi lowercase t over capital T. So here we have a sinc with an amplitude of 1 and the 0 crossings are at multiples of capital T. So here we have t, negative t, 2t, negative 2t, and so on. In class activity 2, find the Fourier transform of x of t equals e to the negative at u of t, where a is greater than 0. So x of j omega is equal to the integral from 0 to infinity. And notice the integral is from 0 to infinity because this is u of t, which means it's 0 before time 0. E to the minus at, e to the negative j omega t dt. So combining the exponentials, I get the integral from 0 to infinity, e to the negative quantity, a plus j omega t dt. Finding the integral, I have 1 over negative a plus j omega, e to the negative a plus j omega quantity times t, evaluated from 0 to infinity. And finally, the Fourier transform is 1 over a plus j omega. In class activity 3, find the inverse Fourier transform of x of j omega equals 2 pi delta of omega minus omega naught. So x of t is equal to the integral from negative infinity to infinity x of j omega e to the j omega t d omega over 2 pi, which equals the integral from negative infinity to infinity 2 pi delta of omega minus omega naught e to the j omega t d omega over 2 pi. Using the shifting property, this integral becomes e to the j omega naught t. So what we have here is that a single complex exponential with frequency omega naught becomes an impulse function shifted in the frequency domain with an area under the curve of 2 pi. In class activity 4, find the Fourier transform of x of t equal to cosine of omega naught t. The first thing we're going to do is use Euler's identity to rewrite this as the sum of complex exponentials. So it's going to be 1/2 e to the j omega naught t plus 1/2 e to the negative j omega naught t. We already know the Fourier transform of complex exponential because we did that in class activity 3. So this becomes pi delta of omega plus omega naught plus pi delta of omega minus omega naught. So what you see here is that each frequency component of the signal appears as an impulse in the frequency spectrum. Note that duality means that time and frequency domain representations sometimes have a relationship. So for example, we have seen here that the Fourier transform of delta of t is a 1, and conversely, the Fourier transform of a 1 is 2 pi delta of omega. So we know that those are duals of each other because the impulse is related to 1 in the time and frequency domain. There's another set of duals between the rect and the sinc, and it is that the Fourier transform of rect of t over capital T is capital T sinc of omega capital T over 2 pi, or the sinc of t over capital T in the time domain. In the frequency domain is capital T times the rect of omega t over 2 pi. Also note that increasing t for the rect and the sinc gives a wider pulse in the time domain and a narrower spectrum in the frequency domain. Response to an LTI system. Given the following linear time invariant system, where the input is x of j omega, the output is y of j omega, and the system has a frequency response of h of j omega. For an arbitrary input, when we were doing Fourier transforms, we had that the summation as k is equal to negative infinity to infinity of x of jk omega naught e to the jk omega naught over 2 pi yields an output of the summation from k equal to negative infinity to infinity x of jk omega naught h of jk omega naught e to the jk omega naught t omega naught over 2 pi. So as omega naught goes to 0, this becomes our Fourier transform, which is the integral from negative infinity to infinity x of j omega e to the j omega t d omega over 2 pi, which is x of t, which becomes the integral from negative infinity to infinity x of j omega h of j omega e to the j omega t d omega over t pi, which equals the integral from negative infinity to infinity y of j omega e to the j omega t d omega over 2 pi, which is y of t. So this is how we go from the time domain to the frequency domain to find the response to an LTI system. And this relates to what you learned in ECE204 and 205, which was AC circuits and systems based upon y of j omega is equal to x of j omega times h of j omega, where y of t is the inverse Fourier transform of y of j omega. Notice this also relates to Laplace transforms, which you discussed in ECE205, where y of s is equal to x of s times h of s, and y of t is equal to the inverse Laplace transform of y of s. And this concludes lecture 5-2 on Fourier transforms.